All right. So last time we started talking about hypothesis tests, and we talked about hypothesis tests in terms of two hypotheses, the null hypothesis and the alternative hypothesis. Null hypothesis is basically the status quo, what people are currently thinking about a research question, and then the researcher comes up with an alternative possibility. So that's and then we talked about the symbols for both hypotheses. We also talked about how to determine when to reject the null hypothesis. And we used this mathematical number called the p-value to come up with an idea of when we should be rejecting the null hypothesis and accepting or supporting the alternative hypothesis. I'm going to actually share the screen with you to the textbook. Just give me a thumbs up if you see the book. Good, thank you, Danielle. All right, so let's just continue from last time. We're just going to do a couple of examples, and I'm actually going to go into StatKey and show you how to create a what's called a randomization distribution, which is what StatKey uses to simulate a hypothesis test. All right, so let's actually scroll up a little bit. I don't want to do this one yet. Okay. Yeah, the one that we did last time was the one about the light, if you remember. There were mice who were exposed to light or no light at night, and there was this hypothesis that those who were exposed to light would gain more body mass or weight than those who were not exposed to light at night. So let's actually find this. Actually, what I'm going to do is go into StatKey and show you this particular case. Just give me a second here. I'll stop sharing. And we go into StatKey. All right. There we go. All right, so there's StatKey. And on the right side here is, on top right here is what they call randomization hypothesis tests. So the case where we were looking at that experiment with the mice, I believe is in this test for difference in means. I'm going to click that. And they have a bunch of data sets for this section, but scroll down, I believe you can find the mice. Here it is. Mice weight gain, light versus dark at night. All right. So off to the right here says gives the original sample. The original sample had, I believe, let's see, 4, 6, there were 8 mice who were in the group that got exposed to light at night. And then there was, maybe there was 10 of these. 6. Yes, there's 10 of those. And then there are 8 who were not exposed to light. There's just regular dark conditions at night. Mice were sleeping. So these two numbers here, this is the mean of those 10 mice in the light group, and this 4.114 is the mean of the 8 mice in the dark group. So if you subtract those two numbers, you get 2.618, I believe. 2.618 is the difference in their means. Now, the null hypothesis in this case is there's no difference in the two groups. It doesn't matter whether the mice are exposed to light or not, or no light. It should not have any effect on their body mass. And the alternative hypothesis is that the light group should show greater mass than the dark group. So automatically in StatKey, the null hypothesis states mu1 is equal to mu2, which means the two population means are equal. And by the way, that also means that mu1 minus mu2 is equal to 0. If they're equal, then when we subtract them, we should get 0. So that's the null hypothesis. Now the question is, what is the alternative hypothesis? Is that the light group is greater, should have a greater mean than the dark group. Now, when we have a greater than symbol in the alternative hypothesis, greater than, it means that we're going to do what's called a right tail test. We're going to look at the right tail of the randomization distribution. So I'm going to click right tail here, and I'm going to generate 1,000 samples. Okay. All right. Now, what are these samples? Each one of these samples is like the original sample, except it has different means for the light group and dark group, right? And the way the stack key does this is it assumes that the null hypothesis is true. In other words, the middle average is about 0. All right, so notice the null is 0. All right, and each of these dots represents a sample of how many mice? 18 mice, 10 in the light group and 8 in the dark group. Okay, but they all have different means. Now some of these numbers down here, you can see, are negative. That means that for those groups, for those samples of 18 mice, the dark group actually showed more weight gain than the light group. And then the positive ones show that the light group has gained more weight than the dark group for those samples. Now, when you click the right tail here, it automatically gives you 2.5% on the right. All right, 2.5% of the 1,000 samples. And that's 25, by the way. If you multiply 1,000 times 0.025, there's 25 right here. But defaults to that, but that's not what we're interested in. What we're interested in is what's called the p-value. That is the number of samples here that are at least as large as the sample difference in means. And remember, the difference between the original sample mean for the light group and the original sample mean for the dark group is 2.618. So the way to actually come up with the p-value is very easy. You just go down to this bottom number here and just click it and type in the actual sample statistic, 2.618. Right, I'm going to hit enter. And notice what pops up here is 0.01. In other words, 1%. So 1% is the p-value. 1% of all these dots here are samples where the difference in the means between the light group and the dark group is at least as large as or larger than 2.618. Okay, so that is the p-value. That is what we're looking at, and it's very small. So in many circumstances, as you'll find out, we'll end up saying, well, if the true difference in these two means is 0, but we got a sample that has a difference in the means of 2.618, then the chance that this is just normal that this particular sample is just normal variation, normal chance when the difference in the means is 0, well, the probability of that happening is 1%. That's really small. So this is sort of evidence against the null hypothesis, because if the null hypothesis is true, then there's only about a 1% chance of getting this particular sample. And that's really small. So the smaller the p-value, the better chance is that we're going to end up rejecting the null hypothesis. But at the end, by the end of today's meeting, I'm going to show you a method which you can absolutely determine if that p-value is enough to reject the null hypothesis, okay? And it'll be a few minutes from now. It's actually in 4.3, but I'm doing a little review of section 4.2 now. So this is how you do it in StackKey. You basically determine the alternative hypothesis, okay? And then based on whether the alternative hypothesis is less than, greater than, or not equal to, determines what type of tests that we do, right? Now, If it's greater than in the alternative hypothesis, we use the right tail test. If the symbol in the alternative hypothesis is less than, we use the left tail test. And then if it's not equal to, we use what's called the two-tail test. And we'll do an example of the two-tail test in a few minutes. All right, anyway, I'm not going to test you on using these randomization tests, but they are useful to trying to understand exactly what a p-value is and why a lower p-value rejects the null hypothesis, okay? Any questions about this? And by the way, you can, take the examples from the book, find the data set in Stackey. Hopefully it's there. And you can play around with this. You can come up with different number of samples. You can come up with a different alternative hypothesis, things like that. You can always play around, right? Can't break it, okay? So let's now go back to the book. I'll stop sharing here. All right, so let's find another example. This is an example where the alternative hypothesis was greater than. That's the light and blue group. Let's see if we can find another example here. Here's one right here. I believe this is also in Stackey. All right. Let's say, all right, now it says here in a student survey, 250 students were asked to write down a 4-digit random number. Only 12 of the 250 numbers ended with 0. Does this provide evidence that hold on one second, please. All right, sorry about that. All right. All right, now, it says here 250 numbers were basically selected at random. Only 12 of them ended it with a 0. Now, if a digit, this should make sense to you, a digit for any of the 4 digits in a 4-digit number could go from 0 all the way up to 9. So if it was equally likely that a particular digit would show up in a 4-digit number, it would be a 1 out of 10 chance that you would get that particular number, because 0 to 9, there's 10 numbers, and it should be a 10% chance. So the fact that you got 12 out of the 250, and actually, if you calculate that with a percentage, hold on one second. You can also follow along with me and calculate this. That's 4.8%. All right. So 12 out of 250 numbers ended with a 0. But we would expect around a 10% chance of getting a 0 at the end for the last digit, but we're actually getting 4.8%. So the question is that a significant result? Is that sample prove that zeros are used less often for the last digit of a 4-digit number? Okay. Hopefully that is clear to you. So if you scroll down here, you see the alternative hypothesis, excuse me, the null hypothesis, H sub 0, is that P is equal to 0.1, right? And that would be the case where we would expect any number to be the last number in a 4-digit number to be a 10% chance. There's a 0.1 proportion. The alternative hypothesis is that people tend to use zeros less often when they come up with a 4-digit number, and therefore the P is less than 0.1. All right, so that's the alternative hypothesis, is that there's something going on here. It's not, these numbers aren't being picked randomly, and people tend to use 0 less often than other numbers for the last digit of 4-digit number. All right, so we'll go back to Stackey. And actually, I don't think I was actually sharing that. I apologize. So go back to, okay. Yeah, I think somebody was actually telling me here that you share the screen. Sorry about that. So let me go back and share the screen. I got a little distracted before, so let me just go ahead and do that. Just give me a second. I'll just hold 1 second here. Actually, can somebody just yell out, can you see this page right now? Yes?
Yeah.
Yeah, I'm sorry. All right. So it wasn't showing before, and now I'm showing. Okay. So this is the problem right here that I was just referring to. It's in your textbook on page 301. Okay. And again, I'll just repeat what I've said just briefly. So this was a student survey. 250 students were asked down, I guess they were randomly selected, were asked to write down a 4-digit random number. It says here only 12 of the 250 numbers were ended with a 0. Now, we would expect on average that 10% or about 25 of those numbers should be end in 0, because there are 10 numbers from 0 to 9, and you would think randomly it would be a 10% chance that any number, including 0, would have a 10% chance of being selected as the last digit in a 4-digit number. But in this case, only 12 of the 250 numbers that were chosen ended in a 0, which is actually a 0.048 or a 4.8% chance. So the question is that a significant result? Is it really true that people tend to pick zeros less often for the last digit of a 4-digit number? So the null hypothesis is that we would expect that the proportion of zeros would be 10% or 0.1. But the alternative hypothesis is saying, well, maybe people tend to pick zeros less often for some reason, and therefore P is less than 0.1. Okay. Let's actually go to StatKey and find this particular case. Just give me a second here. All right. So we're just going to go right back out here. Just move this away. I'm going to go back out of out of the screen here. Now, this is a single proportion question. What we just did a few minutes ago was difference in means between two populations, light group and the dark group. Here, we're just looking at one proportion. So we're going to do a test for a single proportion. Now, let's see if we have that random number ends in 0. Here it is, right here. It's the second choice. All right. Now notice again, in the original sample, 12 out of the 250 had a 0 in their 4-digit number as the last digit, which is a proportion of 0.048. That's 12 divided by 250. Now, what is the null hypothesis? The null hypothesis is that P is equal to 0.1. Notice that in all of these examples that you'll see in the proportion test for a single proportion, it always defaults to 0.1. So I have to change that and say that the null hypothesis is P is equal to 0.1. All right, so there we go. All right, now the alternative hypothesis is that says that P is less than 0.10. So that is a left tail test. So I'm going to click left tail. Okay, I'm going to generate 1,000 of these randomization samples. Once again, notice that the p-value or this area here defaults to 0.025. So what it means basically is that we have to type in down here the actual sample proportion. Type that in as 0.048. And again, I want to see what proportion of these samples has a proportion of 0.048 or smaller. In this case, for a left-hand test, we would say or smaller. And notice here, we only have, looks like just one sample here out of 1,000. Only in this particular case, only one sample out of 1,000 is 0.048 or smaller. And therefore, the p-value is 0.001. That's really, really small. So this particular sample is so extreme that if we assume that the null hypothesis is true, that is p is equal to 0.1, the probability of getting 0.048 as our proportion is 0.001. It's 1/10 of 1%. It's really, really small. And so in most cases, we would end up rejecting the null hypothesis that p is equal to 0.1, and this sample supports the idea that the true population proportion is probably less than 0.1. Okay, so here's another example. This is called a left tail test. Any questions about that? Again, the homework that I'm assigning for this, you'll see pictures like this. You'll see pictures of randomization distributions of samples, and they'll ask questions about it just like you. All right. So you'll want to have to create. Yeah, go ahead. Yes.
Why do you use 0.048 for the like the endpoint?
The left endpoint.
Yeah.
Why am I using it? Oh, you mean the right endpoint from going to the left?
Yeah.
That's the sample proportion. See, what a p-value is the probability or proportion of samples, all possible samples, that are at the sample statistic or something more extreme than that. All right, assuming that the null hypothesis is true. So in this case, the null hypothesis is 0.1. The sample proportion is 0.048. Now the alternative hypothesis says p is less than 0.1. Okay, that's the alternative hypothesis. So we're going to look at the left tail and we're going to plot the actual sample proportion. That's why we're making a 0.048, because the definition of a p-value is what's the probability of getting that particular number or something more extreme. In this case, less than that number because it's left tail. Okay, so that's why you have to plot it there. Does that make sense to you?
Yeah, it does. Thank you.
You're welcome. All right. So that is that is called the p-value, and so that's how we calculate, or we're actually not even calculating it. That's how we get the p-value using Statke, the so-called randomization tests, these randomization distributions. What you're going to be learning starting on Monday and going into next week and the week after that, and when we get to chapter 6, we're going to be using formulas to calculate the p-value. Here, what we're doing is we're simulating the p-value, coming up with the p-value through simulation. But as far as our test number 3, and as far as the final exam is concerned, you're going to be using formulas in your calculator to come up with all of that, which I will explain when we get to that point. But here, what I like about this particular book and Statke is that you can grasp the concept of a p-value without actually knowing any formulas. And I think that's important for any student who's first learning this, to see a picture of it before they actually start using formulas. Because once you get to the formulas, sometimes people tend to get caught up in all the details of the formulas and forget about exactly what they're doing and what they're measuring. So your question was very, very good, because what you were really asking was what is a p-value? That's what you were asking. And why are we using 0.048? And the answer is because the p-value has within it the definition that we have to use the sample the original sample's statistic in determining that p-value. All right. So thank you for that question. I want to also show you an example of a two-tailed test before we get to our next section, which is section 4.3. So once again, I'm going to give me a second here. Stop sharing. And we'll go back to the book. All right, so let's find an example of what's called a two-tailed test where the alternative hypothesis has not equal to. Well, here's one right here. All right. So let's read it. It says a Pew Research study in 2015 asked 2001 US adults whether they play video games on a computer, TV, gaming console, or portable device like a cell phone. So obviously this is really old study. It's 20 years old. So you have to bear with it. Obviously people use technology more than they used to. But anyway, in the sample, 501 of the males and 477 of the, so 501 of the 1,000 males and 477 of the 1,001 females said that they played video games. So those are the sample proportions. So the question is, does this provide evidence of a difference in the proportion playing video games between males and females? Now, notice here, they're not saying that in the research question, they're not saying males have a higher proportion who play video games, all right, than females. They're just saying, does this provide evidence that there is a difference between the two groups? So when you see words like difference, all right, as opposed to greater than or less than, you know you're dealing with a two-tailed test. That is, the alternative hypothesis is not equal to. So for example, if you look down here in the null hypothesis, it says PM. Now P is the proportion of males, right? And PF is the proportion of females. So the null hypothesis says there's no difference between the proportions of males and females. PM is equal to PF. The alternative hypothesis says there's a difference, okay? And so it's PM is not equal to PF. So this is called a two-tailed test. Now, what are we going to do? Well, let's see if we can find this particular case in StatKey. All right, so it's a video game example. So let's go back to StatKey. All right, now this involves two proportions, difference in two proportions. I'm going to click this one here. That's the difference in two proportions. Let's see if we can see the video game on here. And it's actually right here. Play video games by sex. All right. All right, so here along here is the original sample. You can see it right here. You see the male proportion, 0.501. That's 501 divided by 1,000. The female proportion is 0.477. That's 477 divided by 1,001. And you can see the difference in proportions between the two groups is 0.024. All right. Now, the null hypothesis is no difference between the two groups. Now, group one, by the way, is the males, and group two is the female. All right. So this is called a two-tailed test because the alternative hypothesis has not equal to. So we're going to click two-tail in this case, and we'll create 1,000 of these randomization samples. Now, once again, this is really important to understand. It defaults to 0.025 on each tail here. Now, because it's two-tail, there's going to be two places where there's red. Now, in this particular case, the sample difference is positive. See, the null difference is 0 because the null hypothesis says there's no difference between the two groups. Therefore, the difference between them is 0. Difference between their proportions is 0. But the sample actually has a positive number. Now, if it was negative, we would come in and change this left tail number here because it's negative. But since the difference of proportions is positive, we're going to go to the right tail, this one here, and change that to 0.024. Okay, we'll click OK. All right. So this is a little different than the other two cases that we were looking at, the left tail and the right tail cases. This is where we now have two tails. Notice that the number up here is 0.157, but it shows the same number on the left. Now, the p-value in a two-tail test, you should write this down, is going to be 2 times this 2 times 0.157. All right, because it's two-tail, it means either to get this particular case, to get a sample at least 0.024 or greater, probability is going to be 0.157 times 2, because there's also a left tail out here also, right? So when we say 0.024 or more extreme, we're really, maybe it might be a little too confusing for you, but what we're really saying is that we want to find something, the absolute value of 0.024 or more extreme. But for those of you who are not mathematically inclined to think like that, we would just say that when you get a calculation, if you get Stackey to come up with 0.157, notice the number's the same on the left, you simply add these two numbers or just multiply 0.157 times 2. And that is the p-value. So for a two-tailed test, all right, you need to take one of those numbers, the 0.157 number here, and multiply it by 2. And that is our p-value, right? So 0.157 times 2 is equal to 0.314. So 0.314 is your p-value in this case, all right? Because of the fact that you have to consider both tails, not just the one tail. All right. All right. Now, that is a pretty high p-value. So most likely, this would just be due, this particular case of the difference of proportions of 0.024 is probably not far enough away from the null hypothesis value 0 to conclude that 0 is not true. So in this case, we would not reject the null hypothesis. Now, it's very important, and I have to stress this, that it's very important that when we do not reject the null hypothesis, it doesn't mean that the null hypothesis is true. It just means there's not enough evidence with this particular sample to show that it's false, okay? So we never ever say, for example, if you take a test in the final exam, and you have, the core piece where you have to write out your answers, and if you get a case where a hypothesis test where the answer is there's not enough evidence to reject, we would never say there's enough evidence to accept the null hypothesis. We would never say that. We would never say the null hypothesis is true. We just say there's not enough evidence to reject it. Now, let's think about that that analogy I told you last time about the criminal trial. When you have a criminal trial, you're assuming initially that the person is not innocent, is not guilty, all right, is innocent. Now, suppose the prosecutor does a poor job, or maybe there's just not enough evidence for the jury to conclude that the person is guilty beyond a reasonable doubt. So what does that mean? Now, when the judge reads the verdict, he'll say not guilty. But in essence, what you just found is that there's not enough evidence to find that the person's guilty, but it doesn't mean the person didn't commit the crime. It's still possible the person committed the crime. It's just the evidence wasn't enough. or the prosecutor just did a bad job in presenting it. Okay, so it's the same thing in statistical tests. If there's not enough evidence to reject the null hypothesis, we never say the null hypothesis is true. We just say there's not enough evidence to reject it. Right? Any questions about that? So the most important thing to remember about the two-tailed test is that we have to take the number that we come up with, in this case 0.157, and multiply it by 2. All right? Or another way of looking at it is just adding 0.157 to 0.157. But in essence, we have to remember that the answer to the p-value question is 0.157 times 2. All right? And you'll see that in the homework when you have a two-tailed test question. All right, so I guess there's no further questions. All right. Now, let's go to the section 4.3. So we'll go back to the textbook. And we'll share the textbook. And we'll go to 4.3. Now, all right, looks like I have to refresh the page here. Okay, here we go. Let's go to 4.3. Now, here is a definition called statistical significance. It says if the p-value is small enough, then results as extreme as the observed sample statistics are unlikely to occur by random chance alone, which means assuming the null hypothesis is true. And therefore, we say the sample results are statistically significant. And that means we're going to reject the null hypothesis in favor of the alternative hypothesis. Okay? That is what we mean by statistical significance. All right? All right. So again, they give this another example here. And this is an example where we're looking at one mean. And this has to do with arsenic for chicken, average arsenic level. This was an example that we looked at last time. Basically, there is a company that has suppliers for chicken. All right, people that these suppliers provide chickens to this company. Maybe this company's a supermarket. And anyway, the company randomly selects chickens and tests the amount of arsenic. If the arsenic is 80 parts per billion or greater, they're going to say basically stay to the supplier. We're not dealing with you anymore. You put too much arsenic in there. If it's not greater than 80, it's considered satisfactory. Now, the thing is, you could get samples of chickens where the sample mean is greater than 80, but you want to determine if it's significantly greater than 80. In other words, is it so much greater than 80 that that we would think that 80 is not the population of chickens. The level of 80 parts per billion of arsenic is not that population of chickens for that supplier, and it's actually greater than that. So we want to test for that. We just don't want to, if we have a sample that has 82 as the average amount of arsenic parts per billion for a particular sample of chickens, we don't want to automatically tell that supplier, oh, I'm sorry, we're not going to use you anymore. We want to determine whether that's just normal variation around 80, all right, because it's just a sample of chickens, or is there strong evidence that 80 is not the average amount of arsenic for that supplier's chickens? It's actually greater than 80. So anyway, the null hypothesis is that the mean level of arsenic is 80 parts per billion, and the company is interested in whether the alternative hypothesis is true, because if it is true, they don't want to deal with that supplier anymore. And the alternative hypothesis says mu is greater than 80. All right. So let's actually go back to stat key. We'll find this particular one. All right, we'll go back. And this is a test for a single mean. And we want to look for arsenic. All right, and it's the second choice right here. Okay. Notice that the null hypothesis states that mu is equal to 80, which is fine, right? Now, the alternative hypothesis says that mu is greater than 80. Therefore, we're going to do a right tail test, and we'll just generate 1,000 of these samples. Okay. Now, notice the sample. Let's go to the original sample here. Up here, it says the sample mean is 91. Now, is 91 so much bigger than 80 that we want to reject the null hypothesis? So let's actually change this number down here to 91. And check out the p-value. Well, interestingly enough, you might think, somebody might come to the conclusion that 91 is big, so is much bigger than 80, and we should reject the null hypothesis and assume the supplier is not a good supplier. Its chickens on average have over 80 parts per billion of arsenic. But notice the p-value here, 0.126. In other words, the amount of, in this particular distribution, the amount of these red dots here, the amount that are at 91 or above, there's 12.6% of those samples that are at least as large as 91. That's our p-value, 0.126. That's pretty large p-value. So as you'll find out in a few minutes, typically we would end up not rejecting the null hypothesis. In other words, there's not enough evidence here. In other words, 91 is not extreme enough in this case to conclude that the supplier is a bad supplier of chickens in terms of arsenic. Okay. So this is not considered a very low p-value, 0.126. All right. So let's go back. So in this case, we would say, most likely we would say something like, it's not statistically significant, not statistically significant. There's not enough evidence to reject the null hypothesis, right? And therefore we would not necessarily say to the supplier, hey, you supply too much arsenic, we're not going to work with you anymore. All right, so let's go back to the book. All right. All right. So, not enough evidence in this case to cancel the relationship with the supplier. All right. Now, here's something brand new. If we were going to make a determination whether a p-value is too big or too small, right, we have to sort of have a cutoff. We have to say, all right, any p-values that are less than a certain number, we're going to reject the null hypothesis. Any number that is at least as large as that p-value, we're not going to reject it. So we have a cutoff. And this cutoff is called the significance level. And we use the Greek letter alpha to represent it. Okay? So this is something that a researcher determines up front before they do any research, is what significance level are they going to use? What cutoff? So that when they calculate their p-value, they're going to compare it to this significance level, okay? And then by comparing it, they're going to make a decision to reject or not reject the null hypothesis. So here is, right here, so you should put a big if you have a paper copy of the textbook, you want to put a big red mark next to this one. This is very important. This is the determination of whether you reject or not reject the null hypothesis in a formal way. If the p-value that you calculate using your test statistic is less than alpha, the level of significance that was selected before the research was done, then we will automatically reject the null hypothesis. Right? We're going to say that the results are significant and we have convincing evidence that the alternative hypothesis seems to be true. If the p-value, however, is at least as large, that means greater than or equal to alpha, then we would say that the results are not significant and we do not have convincing evidence that the alternative hypothesis is true. And therefore, we're not going to reject the null hypothesis. Okay? Any questions about this decision? So this alpha is going to be given to you in the problem. Because typically I have students say, how do I know what alpha is? Because it's going to be given to you. You're not actually a researcher, right? You're a student. So it has to be given to you in any hypothesis test. Here is alpha, all right? Then you go ahead and determine what the p-value is and compare. If the p-value is less than alpha, reject the null hypothesis. If the p-value is greater than or equal to alpha, do not reject the null hypothesis. And that's a clear-cut decision, all right? Period. Clear-cut decision. All right. Now, there was an example here. This is the one we did earlier with the 4-digit numbers, and we were determining if you remember, we were determining if if p was less than 0.1. In other words, what's the proportion of times that a 0 is the last digit in the 4-digit number? We would expect it to be 0.1 just by chance, but we determined because of a very low p-value that it was probably less than 0.1. People tend not to pick zeros that often. All right. Now, if you do remember, the p-value came out to 0.001. I believe that was true. When we did the randomization test in StatKey, I believe we only had one sample out of 1,000 that was the sample proportion, right? I think it was the sample proportion was 0.048. So there was only one sample that was less than that. So there's our p-value. Now, if we picked a alpha of 0.05, 0.001 p-value is much less than 0.05, we're going to reject the null hypothesis. And to be honest with you, most likely anything we're going to pick for alpha, anything that's reasonable, because most people don't pick alphas that are less than 0.001. They usually pick either 10%, 5%, or 1% as the level of significance, or alpha. So even if we picked 0.01 as alpha, the p-value of 0.001 is still less than that. So this is a clear case of reject the null hypothesis, right? The p-value is so low that no matter what alpha we're going to end up picking, most likely we're going to reach the p-value is going to be less than that. All right. So there we go. That's what we do. We just simply determine our p-value, compare it to alpha, which is given in the problem, and determine if it's less than it. If it's less, the p-value is less than alpha, reject. If the p-value is greater than or equal to alpha, we don't reject. It's that simple. All right. So it's not a difficult thing, but I implore you to do the homework with this. All right. I know some of you are not doing homework, but do the homework at least with this, because this will give you practice in using the p-value and comparing it to the level of significance. And eventually it'll just become second nature. You'll know what to do. And it becomes an easy question. It's not a difficult question. It's an easy question to ask whether we're going to reject the null hypothesis or not. All right. Now, in the case of the light and dark groups with the mice, according to the book, I don't know if we came up with this p-value, but according to the book, when they ran their randomization hypothesis test, they came up with a p-value of 0.01. Now remember, this was a right tail test, right? The alternative hypothesis is the light group's mean is greater than the dark group's mean. P-value was 0.018. Using a 5% significance level, are the results statistically significant? All right, somebody yell out if the p-value is 0.018 and our alpha is 5%. Is this a significant result? In other words, are we going to reject the null hypothesis? Somebody yell out, yes or no?
Yes.
Yes, of course, yeah. Because the p-value, 0.01, is less than 0.05. We have to convert that 5% to a decimal, right? So 0.018 is less than 0.05, and therefore we're going to reject the null hypothesis. The results are statistically significant, all right? Now, if we were going to state this in the context of the problem, in other words, not just state that we're rejecting the null hypothesis, we would say something like, there is at the we'd always say state the alpha. We would always say at the 5% significance level, there is enough evidence to conclude that the light group's body mass gain is greater than the dark group's body mass gain. Okay, that's it. So that is the conclusion using the context of the problem. Obviously, that's what you would tell somebody, right? If you were explaining things. Now, let's just look at this one more time. Let's say the significance level was 1%. Now, that's something we selected before we did the research study. Suppose we wanted a 1% level of significance. In that case, would we reject the null hypothesis? Somebody can yell out the answer to that one. Anybody?
It would be no.
No, that's right. We're not going to reject the null hypothesis in this case, because the p-value in that case would be greater than 0.01. So you could see that sometimes the selection of the level of significance determines whether we reject or do not reject the null hypothesis. Now, you might think that's kind of silly, right? Doesn't a researcher just like change the level of significance once they know the p-value? Well, they shouldn't be doing that. That's actually cheating. They should be determining their level of significance before they do the research. And it's usually something that typically researchers in that particular area of study is using, all right? They're typically using 5%, they're typically using 1%, 10%, whatever. It's typically something that's used, and researchers should not be changing the level of significance after they see what the p-value is. So yes, the p-value, the relationship between the p-value and the level of significance alpha can be different depending on what you choose for alpha. And this is an example right here. Now, sometimes the p-value, like in the case we saw earlier with that, with the four-digit numbers, we saw the p-value is 0.001. That's a reject in every case, because nobody chooses a alpha less than 1%. I can guarantee that. 1% is typically the lowest alpha that a researcher will choose. Most researchers in the social sciences, psychology, sociology, economics, they choose 5% as their significance level. I don't see many people use 10%, but I guess there's some groups that use 10%, some groups that use 1%, but it's typically nothing outside of that range, all right? So when you see a p-value that's really, really small, 0.001 or 0.00001, something like that, you can bet that that's going to be a rejection of the null hypothesis. All right, so thank you for that answer. And here's an example here of, let's see, people who were, the proportion who played video games, right? Remember that one? And we ended up coming up with, let me see if I remember, when we did our significance randomization test for this particular problem, the one where we were looking at males and females in video games, I came up with a p-value of 0.314. Notice the p-value in the books is 0.282. The p-values will vary from sample to sample, and also from randomization distribution to randomization distribution. But in both cases, that's a pretty high p-value. And remember, I had mentioned that most researchers don't go above 10% for their level of significance. Alpha is typically never bigger than 10%. So 0.282 is going to be greater than pretty much any alpha a researcher is going to choose. And this means there's not enough evidence to say that males, the proportion of males who play video games is greater than or different than the proportion of females who play video games. Now, it is very important that because the alternative hypothesis says not equal to, that we need to multiply the area that we're looking at by 2 so that we get the proper p-value. All right. We always do that for the two-tailed test. Okay. All right. Any questions? Now, one of the things that you're going to learn, starting to learn next Monday, is when we do a hypothesis test, there's going to be 6 steps that we're going to go through, 6 formal steps. We're not going through those steps yet. We're just talking about the how we come to a statistical decision. Reject, don't reject the null hypothesis, okay? That's all we're doing here. Now, one of the 6 steps is going to be stating the null and alternative hypothesis using the proper symbols, parameters, h sub 0, h sub a, colon, p is equal to 0.3, p is less than 0.3, whatever it might be, all right? Those are what you need to learn how to do. And the homework will teach you how to use the proper symbols for stating the null and alternative hypothesis. So that's going to be step number 1 out of those 6 steps. One of the steps is going to be determining the p-value, and another step is going to be determining the decision, comparing the p-value to the alpha, all right? And then therefore we're going to reject and do not reject the null hypothesis. And then another step is going to be the interpretation using the actual information in the problem, using the context of the problem to come up with the actual interpretation. But we will be doing lots of examples of that, 6 steps, going through each one of them, examples that we do. But for now, just note that we've covered just a couple of the steps: stating the null and alternative hypothesis, determining the p-value, comparing the p-value to the level of significance, and then making that decision. Do we reject or not reject the null hypothesis? And that's it so far. That's all we're doing, okay? Notice in this example here, this is another example in the book. Actually, let me, give me a second here. This is actually in the book also, where we're looking at 2 means. This is a case where we're looking at 2 groups here. This deals with people who are about to receive some sort of discipline for doing something wrong. And they're looking at whether the person's discipline is better, is not so harsh if the person who is being charged with the infraction actually smiles. In other words, they smile to the person who's interviewing them. Does that make a difference? If the person actually smiles, so they get less discipline than if a person doesn't smile. So that's what this is here. And so this is an experiment where some of the students were smiling, some of the students were not smiling. And the null hypothesis says basically that, the leniency score is basically how lenient is the person who's doing the punishment, providing the punishment, how lenient are they going to be? So the whole idea here is that there's going to be the null hypothesis says there's no difference. It doesn't matter whether this person smiles or not, they're going to get the punishment based on what they did. And the alternative hypothesis says there is a difference between whether a person smiles or doesn't smile. There is a difference in what kind of discipline they get, right? So anyway, there's various scores for determining leniency, and the average score for the smiling group is X bar S here, and X bar N is the average score for the non-smiling group. And notice that the leniency score is greater for the smiling group. So anyway, let's actually go into StatKey and just do this example. I just want to refresh your memory about multiplying the p-value by 2. This is a two-tailed test, just like we did earlier. So let's just look at this example. A second here. All right, so let's do that example. This is the difference in means. And actually, it's the very first one here. It's leniency and smiles. Here is the data that we just looking at. And actually, we did this, didn't we? We already did this. We just did this example. Leniency and smiles. I think we did. No, actually, we did. We didn't do this one. But the difference here is 0.794. 0.794 is the difference between these two average leniency scores, between the smiling group and the group that was not smiling. This is a two-tailed test. Generate 1,000 samples. And then, because this is a positive difference between these two groups, 0.794. It is 794. We're going to type that in here. 794. Click OK. And so this 0.021 is not the full p-value, because this is a two-tailed test. We need to multiply this number by 2. So 0.021 times 2 is 0.042, and that is the p-value. All right. So I just want to refresh your memory that there is two tails that show up in a hypothesis test when there's not equal in the alternative hypothesis. There's two tails that show up. That's why it's called a two-tailed test. And then we see that there's a 0.01 here, 0.01 here. We simply multiply not 0.01, 0.021. We multiply 0.021 by 2, we get 0.042. Right, that is the p-value. And then if we go to the textbook, they get something a little bit different, but it's the same idea. Back to the textbook. There we go. Now this is slightly different. They have 0.046. That's probably because they have a different randomization distribution they came up with. But it's very close to what I came up with 0.042. And that is the p-value. All right. So if the level of significance is 0.05, do we reject or not reject the null hypothesis? What's the answer to that? P-value is 0.046 in this case, one we're looking at here. And if the level of significance is 0.05, what is the answer? Do we reject or not reject the null hypothesis?
You reject it?
We reject it. That's right, because the p-value is less than alpha. Okay, good. All right. Now, let's go to sections 4.4. Now, sections 4.1, 4.2, and 4.3 all have homework. If you go into Wiley, you'll see that there's assigned homework in there for those 3 sections. There is no homework, however, for section 4.4. Okay, 4.4 has no homework, but you are responsible for couple things in here, and that's what I want to bring to your attention before we leave today. Now, this box that we're looking at here has to do with the possibility that when we make a decision, a statistical decision, it's possible we made an error. All right, it is possible we've made an error. Just like in a court case, if we decide to reject the idea, if we find that there's enough evidence to reject that the person is not guilty, and therefore we will find that person to be guilty. All right, looks like there's somebody who's chatting. I'm not sharing again. Am I not sharing again? Do you see this? Say yes if you see it.
I see it.
Okay.
I see it.
All right. So somebody said I'm not sharing. All right. Anyway. All right. Now, so there's a possibility that when the evidence is presented and you reject the null hypothesis that the person is not guilty or innocent, and you convict them, it is possible the person's innocent, right? We know cases like that. We've heard of cases like that. Somebody goes to jail and then maybe 30 years ago, and then they're still sitting in jail. And because of new technology, such as genetic tests, they've determined that the person was put in jail incorrectly, right? So that's an error. That's a big error for that person, right? Who's sitting in jail. It's also possible that we find that there's not enough evidence to find the person to be guilty, and yet that person did commit the crime. So there are two types of errors. Now, in this box here, we see a 2x2 table. Along the side here is what they call reality. Reality is what's actually true. Now, unfortunately, because we're doing statistical tests, we don't really know what reality is. But reality is basically one of two things. Reality is that the null hypothesis is true, or the null hypothesis is false. All right? That is reality. All right? It's either one or the other. However, we don't know because it's unknown. So what do? We do a statistical test and we make a decision. So the decision up here is one of two decisions. We either have enough evidence to reject the null hypothesis, or we do not have enough evidence to reject, and therefore we do not reject the null hypothesis. Okay? Everybody clear on that? Yes? I think yes. All right. Now, notice here that if the null hypothesis is true and our statistical decision is do not reject the null hypothesis, then we've made a correct decision, haven't we? That's called no error, right? If the null hypothesis is true and we don't reject it, we did a good thing. Also, if the null hypothesis is false and we reject it, that's also true. That's also a correct decision. So where do the errors come? The errors come in two forms. If we reject the null hypothesis, but the null hypothesis is actually true in reality, that is called a type 1 error. All right, type 1 error. So in the case of the person who committed the crime, or the person who is being charged with a crime, if the jury thinks there's enough evidence to convict the person, in other words, to reject the null hypothesis that the person's innocent, but yet the person is actually innocent, that is a type 1 error, right? We reject the null hypothesis when the null hypothesis is actually true. That, by the way, is the same thing as alpha, the level of significance. So that is something you might need to write down, that the level of significance is the type 1 error, all right? The level of significance is the type 1 error, alpha. All right? Now, the other error happens if we do not reject the null hypothesis when the null hypothesis is actually false. That's an error too. That's the case in the case of the jury trial. That would be the case where we say there's not enough evidence to convict, and yet the person did commit the crime. All right? That is called a type 2 error. Type 2 error. And by the way, just so that you know, the Greek letter used for a type 2 letter is beta. It looks like a B. You're probably familiar with beta. So alpha, or the level of significance, is the type 1 error. Beta is the probability of a type 2 error. Right? And I should clarify. Alpha is the probability of a type 1 error. All right. So the level of significance is the probability of a type 1 error, alpha. Beta is the probability of a type 2 error. Now, you do not need to know for this course how to calculate beta. It can be calculated, but it is a little on the complicated side. So you're not going to be asked to calculate it. However, alpha is given in the problem. You never have to calculate it. It'll be given to you in the problem that you will encounter when you take a test, all right, or in the homework. Now, sometimes in medical terms, let's say when you get a COVID test, for example, you've probably heard the terms false positive and false negative, right? False positive, false negative. All right. So what is a positive test? A positive test says that if you got a positive COVID test, that means it's saying that you may have COVID. All right. That's a positive test. A false positive means that you get a positive test and yet you don't have COVID. In other words, the null hypothesis is that you don't have COVID. The alternative hypothesis is that you do have COVID. So you're rejected. So the test is rejecting the null hypothesis, but the null hypothesis is actually true. You don't have COVID. That's called a false positive. All right. And that's a type 1 error. All right. So a type 1 error is also called false positive in medical terms. A false negative means that you get a result that says negative. That means the test is saying you probably don't have COVID, and yet you really do. That's called a false negative, and that's a type 2 error. All right. So that's some additional terminology that's being used here. All right. Type 1 errors, type 2 errors. And I'm going to be going over this some more a little bit later when we review, when I come back from my trip to this conference, when I do review, I will go over some of the finer details about these errors. The important thing to know is, and you might want to write this down, is if you do your hypothesis test and conclude that you're going to reject the null hypothesis, then the only type of error that you could have possibly done is a type 1 error, because the type 1 error says reject the null when the null hypothesis is actually true, right? You've made that type of error. So the only type of error you could make when you reject the null hypothesis is a type 1 error. Sometimes this is being asked on the final exam. If you do not reject the null hypothesis, the only type of error you could make is a type 2 error, because the type 2 error says do not reject the null hypothesis when the null hypothesis is actually false. All right. So make a note of that, depending on what your decision is, determines which of those two types of errors you could possibly have made. All right. And the very last thing, I know I'm keeping you past over a minute or two here, but I just want to bring up one more thing here. Some of the stuff that's in this section 4.4, the problem of multiple testing, you can skip that. I'm not going to test you on any of that. That's why we're not doing homework with this. Publication bias, not going to do that. Replicating results, not going to do that. All right, so skip all of that. This little section here, practical versus statistical significance. Here's the point with this section. You should read through it. Even if you get a statistically significant result, you're going to reject the null hypothesis. It could be that the actual difference that you're seeing is really insignificant. Insignificant. It really doesn't matter. So sometimes when you have statistical significance, the significance on a practical level is not really there. And sometimes it's not worth even doing, coming to any conclusion, because of the fact that practically the effect that you're seeing is not really meaningful, okay? And they give an example with somebody who's taking SAT prep courses, and you should read through it as an example of that. The final thing is the effect of sample size. And here's the big deal about sample size. If the sample size increases and actually becomes so big that and you'll see this through formulas. I'll bring this to your attention when we do formulas. Sometimes if the sample size gets too big, we're going to end up almost all the time rejecting the null hypothesis. So this is something I'll bring to your attention a little bit later. It's just a subtle little thing that they're bringing up here. All right, not something to worry about right now. All right, so it just makes it easier to find significant results if the alternative hypothesis is true. But we'll go over that again later. All right, so that's it for today. And what we're going to start the homework for sections 4.1, 4.2, and 4.3. There's no homework for 4.4. And then next Monday will be remote also. I'll be at that other place. So we'll definitely be doing that remotely over Zoom on Monday, next Monday, the 15th. And we'll be covering section 5.1 next Monday, where we can start introducing some formulas. All right, so that is it for today. Any questions? No questions? All right. So I'll stop the recording and I will see you again next Monday. Send me emails if you have anything you want to talk to me about. And is there anybody here who needs to stay behind and ask a question? Just yell
Yeah,
out. Who is this?
Cammy.
All right. So I'm going to stop the recording, and I don't think it needs to be on the recording.